So let's go back to our area problem. We're going to use RRAM for the duration of these notes. Not because RRAM is the only correct way to do this, but it's the easiest way to do this. We could also use LRAM or MRAM, but the algebra gets a little bit messier, so we'll just stick with RRAM. So we have the function x cubed this time. We're going to approximate the area bounded by the curve x cubed from x equals 0 all the way to x equals 1. And we've got this shape right here that I'm tracing in red. I'm going to try to find the area of that shape, and I'm going to approximate it using 3 subintervals. So if we're going from 0 to 1, and we're taking that interval and we're dividing into 3 equal pieces, then each one of those pieces is going to be 1/3 of a unit, right? We go from 0 to 1/3, 1/3 to 2/3, and 2/3 to 1. So that will be a good first step for all of these problems, is figure out what your delta x is. How big a step are you taking each time you go to the next subinterval? And as we've seen, this is always going to be our width for our rectangle, and that's going to stay constant. Again, it doesn't have to stay constant, but for these problems we tend to let it stay constant because it's easier. Now, if we are looking at RRAM, then we're going to start at the left end, and we're going to take a step of delta x to find our first x value of 1/3. 1/3 is the right endpoint of our first subinterval. That's why we're going to use that as our first x value. We take one step from the left endpoint. The step size is delta x, or the width, and is going to take us to the right endpoint of our first subinterval. And after we get to the right endpoint of our first subinterval, we're going to take one more step of the same size to get to the next right endpoint of the next subinterval. And we'll take one more step, and we're just going to keep on stepping until we get to the right endpoint of our entire interval, in this case 1. The height changes for each of these rectangles because our function is changing. So we've got our height when x equals 1/3 is 1/27, 1/3 cubed. Our height, that's this value right here, 1/27. Our height when x equals 2/3 is 8/27. That's 2/3 cubed. That's this value right here. Oops, that's 8. And then this last height is 1. That's this height right here. So to find the area of each rectangle, we're going to take the product of the height and the width. We'll do 1/3 times 1/27. We'll do 1/3 times 8/27. We'll do 1/3 times 27/27. And then we've got 1/3 times, oh, wait a second, I left something out here. Let's back up and figure out the ith row. So whether I equals 1 or 2 or 3, the x value is I/3. And to find the height, using that x value, we cube it, and we get I³/27. So our generic area is 1/3 times I³/27. So in order to find the area, the approximate area of the region under the curve, we just add up our 3 rectangles. And our 3 rectangles are found using that generic ith rectangle. We've got the sum from I equals 1 to 3, in this case, of 1/3 times I³/27. And when we work that out, I guess I could even just work this out by hand, because 1 plus 8 plus 27 is pretty easy. That's 36. So we've got 36/81, which is, if we divide everything by 9, we get 4/9. And that is an approximation for the area under the curve. It's probably too big because these rectangles stick out quite a bit over the area that we're interested in. So there's all of this area that's extra, there's all of this area that's extra, and then there's this tiny bit of area that's extra. So we know that 4/9 is too big, but at the very least it's an approximation. So if this is an approximation and we're interested in a better approximation, then we've seen that we can increase the number of rectangles. And I did that down here for n equals 4 and n equals 5. You can see that when n equals 3, I'll just rewrite that. We just found when n equals 3, the area was approximately the sum of those 3 rectangles, and it was 4/9, which is about 0.444444444. And we can see that as we increase that value of n to equal 4 rectangles, then our answer is a little bit less than our previous answer. That's less than 0.4 repeating. And that's because it's a better approximation. It's still an overestimate, but it's a better approximation. And then, in fact, if we go to n equals 5, we go even smaller. 0.36 is an even better approximation. Again, it's still too big. We still have a shape like this with a whole bunch of rectangles that are too big by a little bit, but the overage is a little bit less each time. So I guess I should go ahead and put 5 rectangles here. Each one of those overages is a little bit less than the one before it, because the number of rectangles we are using is bigger, so the error is less. We can pick whatever n value we want to, and we can get whatever approximation we're interested in. So we're going to go ahead and do that for the generic value n. So the idea behind finding the generic value n, remember that's the number of rectangles we're interested in finding. And this is still the function. Let's remind ourselves what the function is. We're still sticking with f of x equals x cubed. We're still interested in the area under that curve from 0 to 1. This time we're not going to cut it up into 3 rectangles or 4 rectangles or 5 rectangles. We're going to cut it up into n rectangles. So we've got ourselves this interval from 0 to 1. And how many are we going to divide that up into? Maybe 2, or maybe 4, or maybe 8, or maybe 16. However big we make n, that's going to make our width smaller. So the width is going to be determined by the number of rectangles. And if we take that that interval of length 1, right, the distance from here to here is the total distance. I almost wrote delta. I wanted to write distance, though. Distance between the starting and the ending point equals 1. If we're going to divide that up into n pieces, then each width, each delta x is going to equal that entire distance divided into the number of pieces we're dividing it into. That's how division works. So our width is going to be 1 over n. Remember, it was 1/3 when n equals 3. And it would be 1/4 when n equals 4, and 1/5 when n equals 5. And again, the 1 in the numerator comes from that distance from the starting point to the ending point. All right, and that's going to remain constant for all n of our rectangles. So now we have to determine what is the x value we're going to use. Remember, I said we're going to use RRAM for all of these, just because it's more convenient. So don't use the 0, because the 0 is not the right endpoint of any subinterval. We're going to use the first right endpoint, which is 1 delta x. This is delta x. 1 step of delta x to the right of our starting point. So we're going to have 0 plus 1 delta x, or 1 over n. And then to get to our second right endpoint, we're going to start at the left end, and we're not going to take 1 delta x step. We're going to take 2 steps of delta x. That's going to be 2 over n. That's going to take us to here. That's our second right endpoint. Our third right endpoint is going to be 3 over n, and we're going to continue this pattern until we get to our generic ith rectangle, which is 0. Again, our starting point of 0 plus the number of steps times the length of the step. So this is going to be I over n. And we're just going to continue this until we get to our nth rectangle. In order to find the height, as we've seen already, we want to determine the height of the function. So this is our function, x cubed. So we're just going to take 1 over n, and we're going to cube it, and then we're going to take 2 over n, and we're going to cube it, and we're going to take 3 over n, and we're going to cube it, and we're going to take I over n, and we're going to cube it. We're going to do that for all n of our rectangles. Then we're going to find the area of each rectangle, and we know that we take the height times the width to find the area of each rectangle. So we've got 1 over n times 1 over n cubed. We've got 1 over n times 8 over n cubed. We've got 1 over n times 27 over n cubed. And we keep on going. We've got 1 over n times I cubed over n cubed. And again, this is the area of the ith rectangle. So what do we do with all of our areas? Same thing we've always been doing. We're going to add them all up. So this is the most important rectangle because it's all of them, depending on our value of I. So we're going to take that expression that represents the area of your generic ith rectangle, and we're going to add up all n of them for I equals 1 to 2 to 3 to 4 all the way up to n. And we're going to add them up. We've got 1 over n times I cubed over n cubed. Again, that's the sum of all n rectangles' areas. This looks like something we know how to evaluate, though, because, again, as I starts at 1 and goes to 2 and goes to 3 all the way up to n, the denominator of n to the fourth does not change. We've got 1 over n to the fourth that we can factor out of this sum. The only thing that's left is the I cubed. And if you recall, we've got an expression that we can replace that sum of the perfect cubes with. That's going to be n squared times n plus 1 squared over 4. So we actually have this fairly simple formula we can use for any value of n, and that's going to give us the area approximation over 4n to the fourth. All right, so if I plug in 3 in for n, I should get 4/9 like I did earlier. And if I plug in 4 in for n, I should get, I don't remember what it was, 0.360390363, this one right here. And if I plug in 5 for n, I should get 0.36, and you can verify that if you feel like you need to. But that is the expression for the area no matter what value of n we pick. So it's true for every single value of n. So my question is, what is the best number that we can use? What is the best number of rectangles to use when we're approximating this? Well, the bigger the value, the better. So how about let's use infinity. We're going to use infinity rectangles of infinitely small width. So how do we do that? Well, we can't plug in infinity, but we can use limits. That's what limits are good for. The area is approximately equal to, up here, because we were using a finite value for n. Notice this equal sign. I made it nice and big, driving home the point that this is not an approximation. This is equal to the limit as n approaches infinity of the sum of all of the rectangles from I equals 1 to n of, in this case, we've got I cubed over n to the fourth. And again, we've already evaluated that sum to be n squared times n plus 1 squared over 4n to the fourth. So all we have to do now is evaluate the limit. And again, that's an end behavior question. We have got an n to the fourth is our most significant term on the top, and we've got a 4n to the fourth on the bottom, and that reduces down to 1/4, and that is in fact the area bounded by the curve. That is an exact answer.